All right, so now we'll do question 3. In question 3, Jason gives you parts A, B, and C, and in each of these parts there is an electric potential distribution, kind of in 2 dimensions, with the 3rd dimension being the height of the potential, and he asks you to figure out whether or not the charge distribution is 0 in each of these setups. I'm not going to draw out the setup because it's kind of challenging to do on the whiteboard here, but what I will do is kind of give you some tips and reminders as to know what to do with this problem. So I would do this problem probably second after question 2, just because it's worth quite a bit of marks. It's about 15 marks, I think, for parts A, B, and C combined. And conceptually, it's pretty straightforward if you understand what it's asking you for. And the answers are pretty quick. So if you're able to get something down for A, B, and C, you can actually do this question pretty quickly if you know what's kind of going on and understand the process and what he's asking you for. So he gives you the electric potential, and he says, is the charge equal to 0? So we know that if the charge in the region is equal to 0, that this must then be Poisson's equation with rho equal to 0, which turns into Laplace's equation. Now, the solutions to Laplace's equation, the potentials that solve this equation are unique. As we know from the uniqueness theorem, if there's one potential that satisfies this equation and it solves the boundary conditions, then that will be the only potential that satisfies this equation and solves those boundary conditions. And it's also, the solutions are called harmonic functions. Now, some properties of harmonic functions are that there are no local maxima and no local minima in the solution of the potential. So what that means is that if there are any maxima or minima points in that potential, so any peaks or valleys or anything like that, they have to appear on the boundary. That's the crucial point to this question, is that if we have charge distribution rho is equal to 0, we have Laplace's equation, the Laplacian of V is equal to 0, that means that our solution V to the potential is unique. It's a harmonic function, so there are no local maxima and no local minima. And again, local means that there's nothing max or min inside of the potential distribution you have. All the maxima and minima appear on the boundaries. See if there's anything else here that I want to add. So it's, if I can kind of give you a conceptual way to think about it, to look at it, it's as if you're stretching a sheet over some sort of like metal structure, and when you stretch that sheet across it, the sheet is going to minimize the surface area, and there are going to be no local maxima, no local minima, no peaks and valleys. So if you were to drop a ball at any point on that sheet, the ball would roll off the edge. It would never find a place to sit and get stuck. So there would never be a peak for it to rest on top of perfectly, and there would never be a valley for it to get stuck in. And so again, the stretch of the sheet minimizes the surface area. There's no local maxima minima. It's a harmonic function. Those are the main points to this question. If you understand that, then it's pretty straightforward. So for A, again, I'm not going to draw the distribution, but you can look at the picture and see that there are, again, no local maxima or minima, which means that again we have a harmonic function. The potential is a harmonic function and a solution to Laplace's equation, so indeed rho is equal to 0. For part B, we see that indeed there is a local minima right in the middle. You can see there's kind of a valley that the ball will get stuck in if you were to drop a ball, which means that there has to be some sort of charge distribution in order to cause this depression in the middle of the potential. So we have a local minima, which means that rho does not equal 0. So for part P, the charge distribution in this region is not 0. And finally, for C, again we see that there are no local maxima, no local minima, no local max or min, so rho is equal to 0. For some additional clarification on this, or the idea of the harmonic function, the uniqueness, and the potential, and the kind of the distributions that we're looking at, Jason actually has some information on this in his online notes. So if you look at slides 3.1 on D12, pages 6 to 8, there's pretty much the exact like this exact problem is on there, and he walks you through, kind of shows some pictures of potential distributions, shows that there are no local maxima, no local minima, which means that this is a harmonic function and that rho is equal to 0, satisfying Laplace's equation. So again, if you kind of understand this conceptual stuff, and you can read these notes, and in the textbook there's a little bit of information as well that'll help you kind of get the concept of as what he's asking for. Otherwise, A, you look, there's no local max, no local min, rho is equal to 0, yes. B, there's a local minimum, rho is equal to 0. Sorry, rho is not equal to 0. No. C, there's no local max, no local min, rho is equal to 0. So this part here, answering the questions, could take you a minute if you were able to write quickly and see that there's no local maxima, no local minima. Understanding this, the uniqueness, the harmonic function, and no local max, no local min, that's the key part of this question.